On the soil lab, you're going to make sure you don't have any leaves, sticks, twigs, bark, or any of that kind of stuff. It needs to be the underlying soil that you can actually. Yes, sir.
I still don't know how to use this chart.
The triangulation chart. All right, let's do another one here, and I'll come over here. I'll come over there and show you. And let me address Jeremiah here for a second, and the rest of you guys, because I know some of y'all are new, and a lot of y'all don't know me, and sometimes I can come across as a little bit coarse. Maybe I hit the no button a little bit too much for fun. But I can assure you that I am here to help you, that I care about you, that I'm here to support you and help you to be the most successful person you can be in terms of science. And if you need a recommendation or anything like that, that I am here for you to help you out with that. Don't be afraid to ask questions. The only bad question you can ask, Donovan, is the one I just said the answer to. Meaning if I just said the answer and then you asked me the question and you weren't paying attention, then I'll probably yell at you. But otherwise, if you're not sure about something or how to do something, feel free to ask because I am here to help you to learn and figure stuff out. And I just want you to know that I'm not quite as off-putting as maybe I come across sometimes. Luke can tell you, right? All right, so let's do one more here. Let's say we have 50% sand, 10% silt, and 40% clay. So we're on the triangulation chart on page 224. We've got 50% sand, 10% silt, and 40% clay. See if you can triangulate where that, shh, don't say it out loud, where that comes into play. Okay. Alright, what do you get? Yeah, and so this is probably a little bit easier to see right here though. So you're just coming together where, let's say 50, come this way, 10, come this way, and then 40 this way. So wherever those three lines intersect from the three different sides. So you should be pinpointing about there. Does that make sense? And so what do we get, Caleb? Sandy clay. How much fun would that have been in your house, Sophie, if they named you Sandy and they named Clay Clay and they had named Shelby Silty? You probably thought you had geologists for parents, wouldn't you? That'd be pretty cool. Hold on a second.
Name your kids after rivers, you know.
Who would name their kids after rivers? Okay. Yes. So Sandy Clay, you made any questions about how we got that? How we triangulated those? You will see one of those on the test. All right. Let's see. In the notes, we got down to, we're basically down to part D then, correct? All right. Earth's atmosphere. Turn to page 88 and 89. Switch gears away from the dirt. Joe Dirte. All right, on page 88 and 89, atmosphere. The composition of the atmosphere. What is our number one component in the atmosphere? Nitrogen. In what form? N2. And what percent of the air is nitrogen? Y'all should know this. No. 78%. Good. So 78% of the atmosphere is nitrogen. And N2, it's an inert gas, so it's not reacting with anything else. Okay? So just imagine in our room, we've got, can you imagine if you could actually see gas floating around? That'd be pretty cool. I imagine that'd be a little distracting though. And then the second component of the atmosphere is what? You know, out there on the internet.
Oxygen.
Oxygen. What percent's oxygen? What?
I just said 12. That was just a wild idea.
5. 3. 11.
Who said 30? Well, we already had 78% nitrogen. Oh, you have me confused. 21% roughly. So just about 21% is oxygen, O2. And then the other percent that we have left, about 0.9% is argon, and then probably the other one you need to be familiar with, because I don't really care about argon, nor do I know what it's used for, anything about it, is carbon dioxide. Carbon dioxide makes up roughly 0.04% of the atmosphere.
Really?
0.04.
It'd be so much more than that.
I know, as much as you hear about carbon dioxide. Carbon dioxide is important and significant for what reason? Well, we do breathe it out. It's needed for photosynthesis, but what? In environmental science context.
I said just plant like that's what they take.
I was
It
just
might heat
saying-
up the earth.
Global warming.
Global warming, yes, climate change. CO2 is one of our main, probably the main greenhouse gas. Now, like molecule per molecule, it's not the worst. Methane's a lot worse than CO2 is, but there's much more CO2 put in the atmosphere when we burn fossil fuels. So we'll get into climate change later on. We'll talk about the greenhouse effect. Now, it's important to note the greenhouse effect in and of itself is not a bad thing. The greenhouse effect is good. If we didn't have the greenhouse effect, what would happen? It'd be super cold at night. We'd all freeze our selves off. So, I'm recording now. So, the greenhouse effect is a good thing. We need the greenhouse gases in order to maintain a fairly stable temperature from day to night when we don't have the sun around. But just like too much of any good thing, Andrew, if you have too many greenhouse gases, then that can heat up the Earth's atmosphere artificially more than it naturally should. And that's where you hear a lot of the issues related to climate change. We'll discuss a lot of those as we get toward the end of, I think really it's the end of the year when we talk about global change.
So is that why it was, is that why a million years ago it was really cold in the ice age?
Because of less CO2. I mean, like a lot more could get locked up. A lot of times, like ice ages and stuff could be caused by like a large volcanic eruption. It could be caused by a meteor. Anything that throws a lot of dust and ash in the atmosphere and blocks out the sun for a while could set into like a cycle of cooling. But typically, like when you think about like dinosaurs and the Earth's covered in swamps and the sea levels are higher, probably CO2 levels were at a much higher point then. Yes, what? You got me. Okay. The Earth's atmosphere, page 89. You need to draw a little triangle and then have the Earth at the bottom and then know what the different layers are from the Earth outward. You don't really need to know the numbers like the distance per se, but you do need to know what the layers of the Earth's atmosphere are. I'm sure y'all probably seen these before at some point. And then we'll go, if y'all draw that out real quick, then we'll go through and talk about those different layers and a couple important things from each one of them.
Is there like an acronym for this?
Yes. Tina sent my thermometer. There we go. You're welcome.
So it's like the ozone layer are mixed with the stratosphere and the troposphere.
Yeah, they didn't draw this very well, Jason. No. The ozone layer is within the stratosphere. They've drawn a little bit of that light gray below the ozone layer, so that's where the stratosphere starts. But the ozone layer is kind of in that bottom portion of the stratosphere. They just did a very poor job of. It looks like they're in between the two, but it's not. It's in the stratosphere. I ate way too much chalk yesterday. I think I looked it up. Did I tell y'all that the Tums are made from purified chalk? Yeah. That's so weird. Don't eat chalk out there that's not approved by the FDA.
Mary Beth has a bad problem with eating expo markers and chalk.
I'm not going to comment on that. The video's running. All right. So, The troposphere, what is its significance?
It's where
That's
the
what we live in.
That's where we live. That's probably the most significant. What else?
weather.
That's where weather is located, okay, in the troposphere. And the one number you may want to know is the troposphere goes from about 0 to 18 or 20 kilometers, which would be roughly about 10 or 12 miles up. And so that's going to have all our weather where we're located almost all the time. Planes and stuff are going to fly kind of in the middle, upper portion of that troposphere, even at the high altitudes. And so that is, and there's more, most of your atmosphere is in the troposphere because of, like most of the actual atmospheric particles are in the troposphere for what reason?
For us to survive.
Well, it's not there for us to survive. That's very egocentric of you, Colby. The atmosphere is here for us. Gravity, yes, that's a good point. Good. Gravity holds those particles closer to the earth. That's what I was going for. Once you get up to about, you don't have to get that far out, but once you get up to about 8,000 feet above sea level, what starts to happen?
Less gravity.
Less gravity? I don't know the gravity change. Less air. Why is there less air?
Because the gravity pulls all of them down.
Yeah, so it gets thinner. So once you go up above 8,000 feet, you start getting into altitude sickness. A lot of people, like if you go out west, go to the mountains somewhere, you're somewhere that's higher up like that, you start getting headaches and your body can start to feel weird just because of the lack of oxygen that our bodies aren't used to. Now, if you live out there all the time, you're used to it. Your body usually makes more blood cells. That's why a lot of people go train at higher altitude so that they get more blood cells. Although when you go back down somewhere else, you typically your body kind of compensates and goes back to normal. So it wouldn't last very long. All right, let's see. Stratosphere. Jeremiah, why is that important? Jeremiah, why is that important? Jordan, why is that important? Ozone layer is found there, yes. So the stratosphere is significant because it contains the ozone layer. Ozone in the stratosphere is good, yes. Why is it good, DeQuinte?
Because it blocks out UV rays.
Yes, so if you look in your book on page 88, on the middle right side there, I'll just read for you here, so this will be easier. Ozone, a pale blue gas composed of molecules made up of 3 oxygen atoms. So ozone is made up of O3. Ozone in the stratosphere is good because it blocks out UVB and UVC rays. It doesn't block out, I don't think, any UVA rays. I don't think there's bad, but one of those, I'll have to look this up. One of those is more concerned with like causing like aging. You know, see people's skin who looks all leathery, like they've been at the beach too much and never put on sunscreen in their life. Looks like a leather belt or something. And then one of those is more a primary cause of different types of skin cancer that we see. There's 3 different skin cancers. So anyway, those are the bad ones, and we will measure UV radiation later on. I've got some probes, and we can go outside. We can measure UVB, UVC rays. I'll probably have you bring in like your sunglasses, whatever you normally wear for sunglasses, and we'll test the probes behind those to see how effective they are. If you've got like a rash guard, you know how like people that surf or that snorkel a lot, or if you swim a lot, there's like they sell these shirts that are like SPF 50, or you go on the water a lot. You know what I'm talking about? Those shirts that already have like kind of a built-in SPF. I mean, all clothes are somewhat resistant to sunlight going through, but the ones that have that extra layer, we can see how many UV rays get through there comparatively. So we'll look at that a little bit later on. But the main thing here is ozone layer. It helps to block out a lot of harmful rays from the sun. Now, you can have ground level ozone. You can have ozone in the troposphere. Ozone in the troposphere is bad. Okay, so ground level ozone, you hear this a lot, like any of y'all that move off to Atlanta or somewhere crazy like that. Atlanta, LA, any big city where there's a lot of smog. Ozone is a byproduct of that. And ground level ozone is harmful to plants, to animals. If you've got breathing problems, it's harmful. A lot of times in those cities, like in the summertime when it's really bad, which is when most of the smog and stuff is an issue, like they will have air quality alerts that'll say like give you the amount of ground level ozone. And so if you do have respiratory issues and you move to a big city, that's something that I would monitor closely because it could affect your overall health. Okay, so ozone in the troposphere, bad. Ozone up in the stratosphere, good. You got a question, Luke? You the man. Mesosphere, who cares? Read figure 4.2 for us, Ashley.
Northern lights.
Yeah.
The glowing moving lights that are visible at high latitudes in both hemispheres are the product of solar radiation energizing the gases of the thermosphere.
Yeah, if you look at the graph there on 89, you'll notice what happens to the temperature in the thermosphere. Blows up. At the top of the page. Actually, let's read figure 4.1 while we're at it. Read that for us, JT.
The layers of the Earth's atmosphere, the troposphere is the atmosphere layer closest to Earth. Because the density of air decreases with altitude, the troposphere's temperature also decreases with altitude. Temperature increases with altitude in the stratosphere because of the sun's UVB and UVC rays on the upper part of its layer. Temperatures in the thermosphere could reach about 1,750 degrees Celsius or 3,182 degrees Fahrenheit.
3,100 degrees Fahrenheit. They're almost 3,200 degrees Fahrenheit in the troposphere. That would be a problem if you're a what?
Person.
Yeah, if you're an astronaut or someone. So y'all probably heard of like meteors that like hit the Earth. Most of the time they do what? They burn up in the atmosphere, yeah. So you have this really high heat and radiation that's occurring in the exosphere and the thermosphere, and most of the time things get burnt up in those layers. The troposphere, though, is a little bit different. It's one of those where the closer you get to the Earth, the higher the temperature is. The higher up you get, the lower the temperature is because of that altitude and the ozone layer blocking out those UVB and UVC rays. Thank you, ozone. Now, we've got an ozone problem where there's a hole in the ozone over the Antarctic. And around the Antarctic, it fluctuates. There's thinning over the North Pole. And so that is something, the stuff that actually makes the ozone thin has been outlawed. CFCs, they outlawed it in 1986. But if you've got like an old refrigerator or an old car or something like that, or even if there's like an old house and somebody goes in and cleans it out and there's like aerosols and sprays and stuff, those things could have CFCs. You send them off to the dump, they get crushed up or something, and then they could release those. And it takes about 50 years or so for a lot of those CFCs to break down. So like you guys will probably be old before we really see like normalizing of the ozone layer. Fortunately for us, the hole is over Antarctica, which is, far away, and there's not many people live around that area. But it is a problem. Do what? Did somebody say something? You say something? Nice shoes.
Which way are the winter winds?
Well, Donovan, the troposphere goes up to about 10, 12 miles. There's 5,000 feet in a mile, so 50,000 feet. I don't know how high weather balloons go. It's a good question. I would suspect they're probably somewhere in the troposphere, though. All right, any questions about, is there anything else on that part? If you guys have a quiz, don't forget by 1 o'clock Monday to complete on the AP Classroom. I'll say 1 p.m. Yeah, because 1 p.m. after that, I'm going to turn it on where you guys can go back in and see which ones you missed and what the correct answer is. All right, that's enough and it's on notes A through E. Monday we'll start watersheds. We'll talk briefly about that, and then you guys will get into the lab. Y'all turn to your lab real quick. You people on the line, let's talk about this. All right. Part 2, we're not going to be able to do, which is on page 3. Okay. Basically, it's just talking about different amounts of nutrients in the soil, and if you have different amounts of nutrients, like what would be the appropriate fertilizer to add for those different nutrients, and I've given you some examples here. Monday, we are going to work around, look on the first page. Soil permeability, blah, blah, blah. You can do this at home with a cup. Basically, we're going to take those white little cups, we're going to fill them halfway up with dirt, we're going to poke some holes in the bottom of them, and then you're going to pour, change number 4 to 40 mils, because the cups are kind of small. You're going to pour 40 mils of water in there, and we're going to see how much water flows through your soil in a minute. If we don't have any water flow through there in a minute, we'll probably let it go for 2 or 3 more minutes. And basically what we're measuring here is the permeability of the soil. Now, you probably guessed it. The more water that flows through it, the more what is in the soil? Sand. Good. So I've never done this, but I was just thinking that it'd probably be a good idea, once we do this permeability section, we may graph that in comparison to your soil type, or the percentage of sand that's in your soil, to see if there's a strong correlation, which we would expect. Okay? So that's one part of the lab you'll get started with. Turn over to page 4. Okay, actually on page 4 here, you need to do this one first. You need to start it because it takes 30 minutes to run. So it won't take but a second to get started. Basically fill up a graduated cylinder. You can do this with a tall cup or glass at home. Fill it up with dirt, and then part of the way with water. You do need alum. Alum is called a flocculating agent, which is a big fancy word or term for it helps light particles clump together. So what's going to happen is when we mix our dirt in there, the sand is all going to clump together and settle out, and then the silt, and then the clay. And so you're going to wind up with 3 very distinct layers, and you're going to be able to measure them on the graduated cylinder. How much sand, how much silt, and how much clay. And then you can use your triangle to figure out what soil you have. Does that make sense? Okay, but it takes 30 minutes to let it settle out. So once you mix it in there, it's going to take a while. So we need to get it started first. You can do the other labs, and then you can come back to this. We're going to do all of our soil lab stuff in those bins over there behind Luke. I'll spread them out around the room because I don't want my entire room covered in dirt on the countertops and in the floor. So let's just try to, for my sanity's sake, try to keep as much dirt as you can in those bins on Monday. Last part of the lab. Turn over to the flow chart. Flow chart. You guys can do this at home on your own. All right. Here's what you do in the flow chart. You're going to be filling of the soil. And basically, it's a yes or no answer. So when it tells you to do something, is it yes, is it no, you go to the next one. This is what like a soil engineer would do. I've seen them do this before, where they like pick up the soil, they fill the soil. Sometimes they smell the soil, maybe they lick the soil. Who knows what they got going on in their heads. But by the time they're done, no licking or tasting of soil on this though. Just a disclaimer, because I'm not, who knows what's in your soil. So once you're done, you should get down to what type of soil it is. Now, you will wind up comparing that to what you got in the graduated cylinder. They should be the same or very close to the same. If not, somebody's done something wrong, okay? That's the lab for Monday. Any questions? You're beautiful. All right, here's what we're going to do the last 15 minutes. We are going to watch another 15 minutes of the Japan killer quake. I would suspect that you're going to have a few questions on a quiz or test about Japan's killer quake. Now, the important thing about this earthquake is, one, there was a ginormous earthquake, one of the largest ever measured, caused a massive tsunami, and then it caused a nuclear meltdown. Okay? So, and then what are the environmental effects of those 3 things on Japan? And then remind me at the end, there's an article, a news article I want to talk to you guys about at the last part of class in here, about the actual radioactive water that they're trying to figure out what to do with now. Okay? All right. Peace out.